So in this video, we'll combine observations of seafloor features, insights that are gained because the ocean depths can be mapped globally and accurately. And we'll examine this phenomenon known as seafloor spreading. This will allow us to resolve this missing piece in continental drift. So we'll examine mantle convection as a mechanism that would allow the continents to drift apart. Then we'll describe evidence for the creation of new oceanic crust at the center of the mid-ocean ridges, driven by mantle convection. Finally, we'll explain the connection between seafloor spreading and hydrothermal vents, which are these really unique environments and ecosystems found on mid-ocean ridges. So remember the theory of continental drift. Around 100 years ago, Alfred Wegener compiled all these observations. These range from the shape of the continents to the alignment of far-flung mountain ranges with similar ages, to the overlapping fossil distribution of freshwater and land-dwelling reptiles, to evidence of tropical environments in cold places like the Arctic, to evidence of glaciers in warm places like equatorial Africa and Australia. But this theory of Pangaea still wasn't accepted when Wegener originally proposed it. And the reason was because his explanation for why this happened, the pole fleeing force, which is again driven by the rotation of the Earth, isn't actually strong enough to move the continents. And actually, just before Wegener's death in 1930, a more plausible hypothesis was proposed. This is based off of convection in the mantle. And we already mentioned convection in the outer core, but this convection process is fairly universal. It happens in the atmosphere, especially during thunderstorms. It happens when you make pasta or eat hot pot. So the next time you do this, pay attention to the way that the water flows. You'll see the existence of these cells of rising water towards the center of the pot. These were at the bottom of the pan, but they're so close to the heat source that they become much hotter than the rest of the water in the pan. So they start to rise. And as they rise, they push out colder water, which, because it's more dense, sinks to the bottom. So this creates this flow where you have upwelling of warm, less dense water and downwelling of colder, more dense water. So the same type of flow was proposed for the mantle, especially in the semi-solid asthenosphere that sits right below the lithosphere. The idea is that this asthenosphere is in a state of convection, where you have heated parts of the mantle. That heat is ultimately from the outer core. As the mantle gets hotter, it becomes less dense, and so this causes it to rise through the asthenosphere. And as it does so, it diverges at the surface. And as it hits the boundary of the lithosphere, it will diverge. So parts of it go to the right, parts of it go to the left. And then there's this downwelling cell that restores the volume that was upwelled originally. So this idea was proposed as a way to move the continents apart, and it would generate something like this island swell in between them. So remember, at this stage, this is just a conceptual model. It's a way to think about how this could possibly work. But really the analogy here is that the continents would be like boats sort of drifting on this semi-solid kind of butter-like asthenosphere. Essentially, these are being pushed by these mantle currents. So because this is just a way of thinking about this problem, in order for it to be accepted as a potential explanation for all of Wegener's evidence for a Pangaea, we need to find evidence. And so the seafloor ultimately became this treasure trove of evidence because it had been recently mapped and had been really unavailable to thinking about this problem previously. But now we can see the existence of this spine through the Atlantic, this mid-ocean ridge. And for one thing, this shows that the overlapping shapes of Africa, South America, North America, and North Africa, and Europe, those overlaps are reproduced sort of this parallel line of the mid-ocean ridge. So this suggests that this overlap isn't just a coincidence. This is evidence that the seafloor could be pushing the Americas apart from Africa and Europe. But then how do you interpret this mid-ocean ridge here? Maybe it's part of a missing mountain chain that was at the surface and then sunk to the bottom of the ocean as the continents drifted apart. So if this is the case, if the mid-Atlantic ridge is really a remnant of this former continent that connected South America and Africa when they were closer together, then you might expect them to have rocks that were of a similar age to these continents. So this is a testable hypothesis. You can date the ocean floor at various points and see if they match the age of the continents. This map here shows the age of continental rocks. It's derived from the same uranium-lead dating system that we talked about in the last module. There are a few other long-lived radioisotopes like potassium-40 that can also be used for this type of dating. But by dating rocks and surface environments from around the world, you can date the age of the continents. The youngest parts of the continents are shown here in red. This is land that's been created over the last 50 million years or so. And it includes places like the Andes, the Sierra Nevadas and the Cascades in Alaska, most of the Alps and the Himalayas, places like Japan and other island arcs throughout the Pacific. Notice how these are all sort of mountainous regions. So they're relatively unweathered compared to most of the other continental crust. At the same time, most of this map looks something like yellow, green, or blue, or purple even. These correspond to ages that are 250 million years old, to around 1 billion years old, to 2 billion, to even 3 or 3.5 billion years of age. So overall, if you add all this up, the average age of the continents is several hundred million years old. But when the same exercise is done for rocks collected from the ocean floor, the average age is only around 60 to 80 million years. The oldest sections of the ocean floor are those close to trenches, around 200 million years old. But the youngest are actually found in the mid-ocean ridges. These are only 20 million years old or so. So mid-ocean ridges are the youngest part of the continental crust, which is not what you would expect if you thought that that was just part of the continents that had sunk to the seafloor after they pulled apart. So what are the mid-ocean ridges then? We can use an additional clue about how this process works. But to do that, we need to think about Earth's magnetic field again. So the Earth's magnetic field is kind of like a bar magnet. There's a north pole and a south pole. And this draws lines of magnetic field that go all around the Earth. But remember that this magnetic field derives from a liquid that's constantly flowing. It's not a fixed metal bar magnet like is shown in this picture. And actually, this undergoes changes from time to time. These are often called reversals, where the center of polarity flips. So now the north pole of this magnetic field is actually in the southern hemisphere, and the south pole is in the northern hemisphere. These are called reversals, but the reason that they actually happen is still being figured out. It seems like the best explanation is that the flow of liquid iron in the outer core is just kind of chaotic. And so the parts of the magnetic field can move based on the flow of the magnetic field. And if there's turbulence or other processes that happen when a fluid is flowing, that can influence the net properties of this magnetic field. But even if we don't know how exactly this happens, we know it does happen. Here's how we know that. So during volcanic eruptions, lavas that flow on land or under the sea are cooled and then they solidify. But as this process happens, some minerals like magnetite, which is Fe3O4, are formed. For some cases where this rock cools way too fast for this to happen, but usually that insulates this other layer beneath it where things cool slower. So as this lava cools, these magnetite crystals form early on, but they sort of just form based on the iron atoms in the immediate vicinity of them. And so they form in random directions. But as its name suggests, magnetite is magnetic. It's like a needle on a compass. And so it will align with Earth's magnetic field the same way that a compass does. So by the time the lava cools, you'll go from this random orientation of all the different magnetite crystals to this solid where all the magnetite are pointing in the same direction. They're aligned with Earth's magnetic field. And after this turns solid, these are sort of fixed in place. They can't reposition if the magnetic field undergoes this reversal. So this becomes this kind of time capsule of what magnetic field was at a certain time. And so the first indication that this was happening on the seafloor was actually picked up by ships during World War II that were using these scanners of magnetic field to hunt for submarines. What they picked up instead were these weird reversals in magnetic field at the bottom of the seafloor. So these ships at mid-ocean ridges observed this striping phenomenon. And so rocks at the center of the mid-ocean ridge would have their magnetite fields pointing a certain direction. And so they would give off this signal that could be detected by these magnetometers that the ships had for detecting submarines. So at the center of the mid-ocean ridge, they would point one way, but then a little distance off, they would point another way. And then further off, they would reverse and go back to the original way. And further off the axis, they would point the other way, and they would reverse again. So there was this record of these magnetic reversals sort of encoded in these rocks. What's more is that there was a symmetry to this. So on both sides of the mid-ocean ridge, these reversals happened at around the same distance from the center. So starting at the center, both sides have the same polarity, and the magnetite that forms in these cooled solids is pointed the same way. But then more magma comes up, these blocks of crust are pushed to the side, and that field reverses. Eventually, that reverse field is also pushed to the side. That's what generates these paler parts. Then a new crust is put in that aligns with the reversed magnetic field. This leads to this process of striping on both sides. But the best way to explain this is the fact that you have new crust being created at the center of the mid-ocean ridge from magma that's being upwelled from the mantle here. So essentially the magnetic fields here are putting a timestamp on when this crust is created. And it's showing that there's this conveyor belt that exists between magma at this mid-ocean ridge center that's forming and cooling into new crust here, being pushed in both directions away from the ridge axis out into the ocean basin. And as more of these rocks started to be dated with these isotope techniques, there's an interesting pattern that emerged. As the ocean crust got older, the ocean floor also got deeper. And this occurred in all three basins. So there's different symbols on this plot here that correspond to the Pacific, the Indian, and the Atlantic Ocean. You can see they're all fairly shallow at the center of the ridge axis. But as these age 20, 40, 60 million years or so, they drop around 2,000 meters. These are the depths of the abyssal plains. This is because there's a lot of heat at the mid-ocean ridge. And the crust, when it solidifies, is still quite hot. But as it cools, it contracts. Because it contracts, it becomes more dense. Again, this is kind of the same thinking that led to the shrinking Earth theory, which no one really thinks is right anymore. But the underlying principle that as things cool, they tend to get smaller, that principle is still accurate. So this ocean crust cools, contracts, and becomes more dense. And because of isostatic equilibrium, it starts pushing down more on the asthenosphere. And so it becomes deeper than it was when it was a warm, new ocean crust. And this relationship has another interesting consequence. What it tells you is that mid-ocean ridges that are spreading relatively slowly should get deeper over short distances. They should be really steep. There should be an abyssal plain with a steep rise to the mid-ocean ridge. In contrast, if you have a fast spreading center, this occurs in the East Pacific Rise, for example. If you have a fast spreading center, then you'll have a more gradual decrease to typical ocean depths. This is because you're generating a lot of new material that's being pushed further away before it's cooling. And so you have a gradual rather than a steep transition to the typical seafloor. Based on mapping these magnetic features and correlating the ages that were determined by radioactive decay, you can generate this large-scale picture of the age of the ocean floor. You'll notice that all the mid-ocean ridges here are colored red. They're all young. There's new crust being generated at every mid-ocean ridge across the Earth. And here you can compare the East Pacific Rise here, which has this young crust spread further out away from the ridge, compared to the Atlantic, where things aren't spreading as quickly. And so this band of red is very narrow. You can also see this conveyor belt action where this crust, as it spreads across the Pacific, becomes older and eventually reaches an age of 150 to 200 million years or so. And then it hits these trenches, and then the crust gets younger again. So you have new crust being formed at the mid-ocean ridges that is disappearing at the trenches that border these oceans. So one of the other really key pieces of evidence for this conveyor belt image of the ocean floor was the spatial organization of earthquakes across the globe. So this map is showing where earthquakes happen, I think, over a 50-year period. And you can see they trace out the mid-ocean ridge really nicely. There's a lot of tectonic activity happening here as new crust is being formed and it's pushing other crust out of the way. But you can also see there's a ton of tectonic activity around these island arcs, like the Marianas, Japan, the Aleutians, Papua New Guinea, the Philippines, Indonesia. All of these have trenches associated with them. They're all very active and have lots of earthquakes. And again, thanks to these maps generated by Marie Thorpe and others, we can see that these ocean trenches really hug the border of these islands. So from these observations, we can outline a much more complete version of this ocean conveyor belt concept. And the fundamental process behind this is convection in the mantle. So you can see this flow path where this relatively hot part of the asthenosphere rises up to the boundary of the lithosphere at the mid-ocean ridge. Remember that this heat ultimately comes from Earth's core, but it has to pass through the mantle in order to get to this point. Because it's hot and less dense, it rises into the mid-ocean ridge structure, but then starts to cool and solidify. This begins the conveyor. So as new crust is created, other crust is pushed out of the way. This is generating these earthquakes marked here as X's in both directions, to the right and to the left. As this crust is pushed away from the ridge, it also starts to cool. And as it cools, it sits deeper on the asthenosphere, and so the ocean depth increases. Ultimately, these are pushed to ocean trenches that sit below island arcs or continents. There's a massive trench that runs along the coast of South America. And as this ocean crust is subducted into the mantle, some part of it melts, rises up, and fuels volcanic activity on the continents or in the islands. Some of this magma formed from the melting of ocean crust can also collect at the bottom of the continental crust and cool very slowly over thousands of years. And this is how granites like those found in the Sierra Nevadas are generated. But this subduction process goes in fits and starts. And so this generates a ton of earthquakes in these regions, and that's why they're so tectonically active. But overall, this is the process that pushes the continents apart. This is this ocean floor that's spreading and pushing the continents away from one another, taking Pangaea and forming the arrangement that we see today. So to summarize, in the middle of ocean plates, along these ridges, there's an upwelling of the asthenosphere due to mantle convection. This produces new ocean crust and mid-ocean ridges, and this crust pushes out in both directions. There's a cooling and contraction of ocean crust as it ages, and this ultimately leads to deeper ocean basins through isostatic adjustment. This conveyor belt ends with the subduction of ocean crust back into the mantle. This subduction is what forms ocean trenches. This process is what keeps the ocean crust a lot younger than the continents, which don't go through this cycle. Remember that different sections of the mid-ocean ridge system spread at different rates. You can infer what those rates are based on the topography around them. Slow spreading rates will be steep, and fast spreading rates will have a broad rise between the abyssal plain and the ridge crest. There's one more thing I wanted to talk about before we finish this lecture, and that's hydrothermal events. You can see, like earthquakes, they're not randomly distributed throughout the ocean. They tend to follow these mid-ocean ridges in both the Pacific and the Atlantic. A number of these events look like the black smoker shown here, where this hot metal-rich water comes shooting out of these holes in the ground. Because it's metal-rich, it turns this black color. So these hydrothermal events form because seawater percolates or diffuses into the ocean crust. This happens relatively far away from the center of the ridge. But as it diffuses further into the crust, it gets close to this magma source, and things start to heat up. This water heats up to around 400 degrees C, and as it does so, it leaches or dissolves a lot of the metals and other materials in the rock here. Also, because it's so hot, it becomes a lot more buoyant, and so it starts shooting straight up out of this ridge valley here. When it emerges from the vent, you can see this dark color, but eventually it mixes with seawater and forms these neutrally buoyant plumes that then spread out with ocean circulation. And you can follow these plumes for thousands and thousands of miles. Actually, this is an example from a research cruise I was on in the South Pacific. This is at the center of the East Pacific Rise, and you can see how the topography slopes relatively gently towards South America and further into the Pacific Basin. You can also see these ups and downs, these wiggles here are individual abyssal hills. Finally, you can see this deepest point, the Peru Trench. What this map is showing are dissolved iron concentrations in seawater. And you can see right at this ridge crest here, this is where the hydrothermal activity is concentrated. This releases a lot of iron into seawater. This plume of enriched seawater is then circulated away from the ridge crest through natural circulation. This is a key process for sustaining life in the oceans because iron is a key nutrient for phytoplankton growth. It's at the center of the photosynthetic complex that they use. And so this hydrothermal circulation that's driven again by the magma source in the asthenosphere is key to fertilizing the oceans from below. So these hydrothermal vents also support these chemosynthetic ecosystems that live right at the edges of the venting. You can see these are two worms, and they have this symbiotic relationship with these chemosynthetic bacteria. They can utilize these chemical gradients that are released from this hydrothermal plume, but are out of equilibrium with seawater. But these don't last forever. And just a couple of years later, a return to this axial volcano shows an eruption instead. This vent's gone, new magma is coming up and erupting. This is new seafloor that's going to be generated here. You can see all the volatile elements escaping. So this is the engine that's pushing the oceanic crust apart. This video, we introduced this idea of mantle convection and how it can potentially lead to continental drift. We also described lots of evidence showing how this mantle convection leads to the spreading of the seafloor, which is the creation of new oceanic crust at mid-ocean ridges. And this pushes the older oceanic crust away from the mid-ocean ridges in both directions. The same process of mantle convection is the energy source that sustains these hydrothermal vents. This is water that's heated and chemically enriched because of its proximity to magma in the mantle. This rushes out into the ocean, supports these really unique chemosynthetic ecosystems, and then releases nutrients like iron into the ocean, which can fuel phytoplankton growth. These are just some of the connections between solid Earth and life in the oceans that will be explored later on in further modules.